Okay, so our next speaker is Stephan Pfannerer from Technical University of Vienna. He's going to talk about an SL4 web basis from hourglass Plabic graphs. Please, Stephan, you can.
Thank you for the introduction, and thank you for giving me the opportunity to talk here. So the title is very algebraic, but I want to focus mainly on the combinatorics, so I thought I'd pick a shorter title, which is 4-row webs. And you already got some idea what it could be about in Anne Schilling's talk. But let's first say this project I'm presenting now is joint work with Jessica Stryker, Oliver Pechenik, Joshua Swanson, and Christian Gates. Let's start with standard Young tableau. I guess many of you are familiar with those. So we take a partition, lambda. Here it's a partition 442, and we make this nice Young diagram with 4 boxes in the first row, 4 boxes in the second, 2 boxes in 1 box. And we fill these with the values 1 up to n, such that the rows from left to right and the columns from top to bottom are increasing. And on this standard Young tableau, there's a nice map. You have seen generalizations of that one before, which is called Schützenberg promotion. And the most classical way to define it is via should it occur, which goes as follows. So we start here with the 1, we delete that cell, and now we have an empty cell. And we want to slide the entries from the right and below into this empty cell, such that we are still increasing along the rows and the columns. So we cannot slide the 3 up because that would make the first row not increasing because of 3 and 2. So we better move the 2. Similarly, now we cannot move the 5 up because then the first row would not be increasing, so we move the 4. At this step, here we cannot move the 10 because then the third column would not be increasing from top to bottom, so we move the 8, then we move the 11, and we end at an outer corner. We fill this with the next possible integer, which is 12, and we subtract 1 from everything and get back a standard Young tableau. And it's actually quite easy to see that this is a bijection on standard Young tableau of some shape to some standard Young tableau of the same shape. So the backwards map would simply be increase everything by 1, delete the 12, and then slide in the opposite direction. And because it's a bijection, people are very interested actually in the dynamics of this map. And in particular for rectangular standard Young tableau, it's quite nice. If we take a rectangle of size n, then if I apply promotion n times, I always get back the standard Young tableau that I've started with. So promotion done n times gives us the identity. And on the slide, on the presentation before, you have seen about the cyclic sieving phenomenon. So it's actually also quite nice that one can describe the full dynamics of this promotion operator by some cyclic sieving phenomenon. So we take a polynomial here. This is the generating function for the major index of a standard Young tableau. So the major index of a tableau is the number, you look at all the descents and you take the sum of the descents. And if you evaluate this polynomial at roots of unity, so we take he to be a primitive n-fold of unity, and we plug in he raised to the power k, we get the number of fixed points of the promotion operator applied k times. I will not talk about this second theorem, although it will also follow from what you will see on the next few slides, but I will only focus here on this apply promotion n times and you get back the identity. So if I see something like this, I apply something n times and get back the identity, I think of diagrams. You have seen them in the talk before, chord diagrams. When you rotate them n times, you get back what you've started with. So we're interested in finding diagrams that are in bijection with our... I'm very sorry that my phone is ringing again. Let me make that silent. Okay, the phone should not be a distraction anymore. So let's jump right to the next slide and you will see what I wanted to say. So let's take a 2-row standard Young tableau, and you have seen this also in Anne's talk a little bit. These 2-row standard Young tableau of rectangular shape are in bijection with non-crossing perfect matchings. So it's easier to describe the bijection going from the bottom to the top. So we take our non-crossing perfect matching and we look at what are the openers and the closers of each arc. So an opener of an arc going from A to B is just the smaller value. So 1 going to 8, then 1 is the opener, and 8 is what we call a closer. Or here 11 going to 16, 11 is the smaller value, so this is the opener, and 16 is the bigger value, so this is the closer. And we, starting with a non-crossing perfect matching, we get a 2-row standard Young tableau of rectangular shape if we write all the openers in the first row and all the closers in the second row. And what's quite nice is if we apply promotion, we get another standard Young tableau. We can look at the corresponding matching, and it turns out that the matchings are just rotated. So if you look carefully what's happening from here to here, you really take that matching and rotate it by 2 pi over 16. And this proves actually the first theorem before, because if you now rotate n times, you definitely get back the same matching as before. And with some algebraic tricks, you can also get this result by Brandon Rhodes giving the cyclic sieving polynomial. So this is the 2-row case. Let's have a look at 3 rows. So there is a nice map by Kovanov and Kupperberg from 1999 that maps standard Young tableau to diagrams that look like this. So let's talk a little bit about what you can see here on the right side. So we still have vertices on the boundary, and the number is the same as the number of boxes in a standard Young tableau. The vertices here on the boundary all have degree 1. And then we have internal vertices, all of them have degree 3. And we see some bipartiteness, so we have black and white vertices. Also here in this theorem says that we get what's called non-elliptic webs. So from all these diagrams that you can draw with these 3-valent interior, 1-valent on the boundary and black-white alternating, you take those webs that don't have squares, that don't have quadrilaterals in the middle. So the smallest face that's allowed is a hexagon. And 10 years after the theorem by Kovanov and Kupperberg, the Peterson, Poliavsky, and Rose proved that this projection actually intertwines promotion and rotation. And this again is kind of a proof by picture for a 3-row standard Young tableau, why applying promotion n times gives you back the tableau that you've started with. And remember, my original title was something about SL4 webs. So these here would be SL3 webs, and there's some huge algebraic story behind it about invariant theory, but I don't want to talk about this algebra too much here. Now the question is what's going on beyond 3 rows. And in Kupperberg's first work from the 90s, he kind of said that the main open problem is to generalize them to higher rank, so to generalize his webs and also the algebraic story behind it to more or less more rows. And this is something that I've done with Christian Gates, Oliver Pechenik, Jessica Stryker, and Joshua Swanson, and we came up with diagrams like this. So I just call them 4-row webs, and what you should see is that we have some boundary vertices, all of them having degree 1. Then we have internal vertices, all of them having degree 4. So before we had degree 3, now we have degree 4. And then we have some edges that twist, and we call them hourglass edges. So they contribute for 2 when we count the degrees. And these hourglass edges, they have a good combinatorial reason to be there, and I want to talk about this now. So what we want to assign to such a diagram is what we call a trip permutation. And first, let's just talk about the first trip permutation. And that goes as follows. You start at some vertex, let's say start at 9, and we want to map 9 to some other vertex. I would think of this as a street network. And these vertices are roundabouts, and the white ones are UK roundabouts, so you turn around left, and the black ones are US roundabouts, so you turn around in counterclockwise orientation. So we start at 9, we enter that roundabout, and because we're now in the UK, we turn left at the first possible exit. Now we're here at this black vertex, so we turn right. Now we turn left again, and we get that 9 is mapped to 13. And if we do this for each vertex, we get some nice permutation. So for instance, 1, if we follow the rules of the road, would go to 4, and 2 will go to 3, and we get a permutation out of this one. So this is the first trip permutation. We can also say, okay, let's not always take the first exit, but we can also always take the second exit. So here, starting at the 9 again in our example, we don't take the first exit, but we take the second exit. We follow the hourglass, we take the first, second exit, and so on, and get that 9 is going to 2. And we do this for all the vertices and record this in a permutation. And the reason to have these hourglasses is really to make this work in a nice way, because if we would not have the hourglass there, we would kind of go into a vertex and go out again and would have some weird loops going on. And we can also say, let's always take the third exit and we get a trip 3. Now there is some definition. So we say that a for-row web is fully reduced if our trips avoid some certain bad double crossings. And you may wonder, if the trips uniquely determine the web, this is not the case, but we say that 2 of these webs are equivalent if and only if they have the same tuple of trip permutations. So let's see what we can do with them. We want to kind of map to standard Young tableau, and there is a really nice map how we get from our web to a standard Young tableau. For this, we need the anti-exceedances of a permutation. Here's kind of the formal definition. It's maybe a little bit easier to imagine if you say, okay, let's write our permutation in 2-line notation. So here we have 1 goes to 4, 2 goes to 3, and over there we have 16 goes to 1. And we look at these elements where the entry in the top row is bigger than the entry in the bottom row. So 16 goes to 1, 1 is smaller than 16, so this is an anti-exceedance. Or here where 15 goes to 2, 15 is bigger than 2, this is an anti-exceedance. So I've underscored these here, and also here and here. And what you can observe is a nice property. So the anti-exceedances of trip 1, here we have 4 of them, in trip 2 we have 8 of them, and in trip 3 we have 12 of them. And also if we look at the sets, here we have 1, 2, 5, 6. Here we also have 1, 2, 5, 6, and some more entries, 3, 4, 7, and 10. And also for trip 3, the anti-exceedance set of trip 3 is is a superset, is a bigger set than the anti-exceedance sets for trip 2. And it actually turns out, if we take a fully reduced web and we look at the anti-exceedances of trip I, this gives us the first I rows of a 4-row standard Young tableau. So applied to this example, 1, 2, 5, 6 is our first row, 1, 2, 5, 6. Then we look at what do we extra get, 3, 4, 7, 10, and these go into the second row. And what we get in trip 3 goes into the third row. And then what's left goes into the fourth row. And this gives us a nice standard Young tableau. And then actually turns out that this is a bijection, and this bijection between the standard Young tableau 4 rows and these equivalence classes of our fully reduced 4-row webs intertwines promotion and rotation. So this again gives a pictorial proof why promotion applied n times to a 4-row standard Young tableau gives us back the identity. And you may want to ask, what's beyond 4 rows? And I can say this is work in progress, but currently we are still hopeful that our approach generalizes. And what you would expect, because for the 3-row case, we had internal degree 3, now with internal degree 4. So the natural generalization is having every vertex to have internal degree 5. That's all that I want to say. Thank you, and I'm happy to answer some questions.